Welcome back to the deep dive. I think we've all had that moment. You pull open the lid on your kitchen bin and you're just hit by it.
Hmm.
That dense, foul, unforgettable smell.
Oh, yeah?
We just call it rotting, or garbage. But what if that moment wasn't just passive decay? What if it was actually a sophisticated, high-energy thermodynamic event happening right there?
That is precisely our mission today. I mean, our source material calls this whole thing the banquet of rot, and we are going to dissect the actual anatomy of that forgotten waste.
So beyond just the surface level.
Way beyond. We're talking biothermodynamics,
Yeah.
chemical warfare, ecological succession, all on a microbial scale. This isn't a slow fade. It's an active, multi-stage engine.
And here's the hook, right? The core scientific idea is that decomposition is fundamentally the triumph of entropy over organized life. Everything we throw away is an organized structure that, well, it just has to fall apart.
Let's unpack that triumph of chaos. It all starts with the second law of thermodynamics. When we look at fresh food, the carbohydrates, proteins, lipids,
Very organized.
extremely organized. They're complex, low-entropy polymers. They're basically little storage batteries for solar energy that was captured through photosynthesis. They're chemically valuable.
And the moment we discard them, that thermodynamic clock starts ticking. Nature just has to relentlessly break down those organized bonds.
It's the entropic imperative. And that reversal, it releases all that stored energy. It converts the complex mass into stable, high-entropy compounds like CO2, water, and mineral salt.
And what's fascinating is that this release of energy, it shows up as actual measurable heat.
It does. We call it waste heat in a thermodynamic sense, but really it's a kind of slow metabolic fire. It's performed by billions of microorganisms. And in a dense waste pile, that heat can raise the internal temperature to a staggering 60 or 70 degrees Celsius.
Wait, 70 degrees? Seriously, that's a 158 Fahrenheit. That is genuinely surprising. My kitchen bin is basically a miniature self-heating bioreactor.
Exactly. Our sources suggest that in really large-scale piles, this biological heat can reach energy densities that rival fossil fuel combustion. It's just delivered at a slower biological pace.
That's wild.
It's a fundamental misunderstanding to think of decay as some cold, passive thing.
Okay, so the sources use a really specific term for how the fate of this waste is decided. It links its future to its burial history, something called taphonomy. Can you unpack that?
Taphonomy, yeah. It literally means the science of burial and decay. It's often used in forensics or archaeology. But here, the taphonomic history of, say, an apple core dictates everything.
So the most critical fork in the road for that waste is what?
The immediate distinction between aerobic and anaerobic environments.
Oxygen-rich versus oxygen-poor.
Exactly. And that's all down to compression and container volume. Aerobic conditions with lots of oxygen give you hot, efficient decay. Think of a well-managed compost pile. It smells earthy.
Right.
But most domestic waste, packed tightly into plastic bags and deep bins, it exhausts that trapped oxygen really fast.
And then we're in that cool anaerobic state, that's putrefaction.
And that lack of oxygen is absolutely critical. It completely changes the entire chemical pathway. It sets the stage for making methane a really powerful greenhouse gas. And those foul mercaptans, the sulfur compounds that define that sharp, pungent stench of old garbage.
So it's the difference between controlled conversion and just chemical anarchy?
Pretty much.
Okay, so once that oxygen is gone, the microscopic cataclysm begins. Our sources call it the microbial vanguard, and they start with enzymatic warfare. But the first stage, even before the bacteria show up, is the organism turning on itself, right? Autolysis.
Autolysis is self-digestion, yeah. The cell's own internal enzymes, they get released and start destroying the cell from the inside out. This releases all these nutrient-rich fluids, which creates the moisture for the real external assault to begin.
And that assault is hydrolysis.
Correct. That's the heavy lifting by external microbes. Bacteria secrete specialized enzymes. So amylases and cellulose break down starches into simple sugars. That's the fuel for the first big bloom of activity.
And the proteins.
Crucially, proteases cleave proteins into amino acids. And this step is vital because the nitrogen and sulfur released here are the direct precursors for the absolute nastiest odors that come later.
And it's not just bacteria. I was surprised to read that fungi are described as the mechanical engineers of the solid phase.
They're the penetrators. Fungi, especially things like white rot fungi, they use their incredibly fine hyphal networks to physically push through the waste. And they're uniquely equipped to break down lignocellulose.
The woody stuff.
The tough, woody parts of plants that most bacteria just can't touch. They tear the structure open, creating access for everyone else.
So let's trace that process in the bin. It's not random. It follows a strict four-stage cascade. Stage 1 is hydrolysis, liquefying the solids. What's stage 2?
Stage 2 is acidogenesis. This is where acidogenic bacteria consume those new sugars and amino acids and turn them into volatile fatty acids, or VFAs.
And that's where things get really unstable.
This is where you get what's called the acid spike. The pH just drops sharply, maybe down to pH 4.
Which is why young waste smells so acrid, so pungent.
Precisely. You are literally smelling those VFAs. Acetic acid, which is vinegar, or much worse, butyric acid, which is famously the smell of vomit.
Ugh. Okay, which brings us to stage 3, acetogenesis.
Right. Specialized bacteria convert those VFAs into simpler stuff, mostly acetic acid, hydrogen, and carbon dioxide.
And that sets up the grand finale.
It sets up the final, and maybe most important, stage, methanogenesis. This is done by strict anaerobes called methanogens. They consume the acetic acid and hydrogen to produce methane, CH4.
So they're making this greenhouse gas, but they're also cleaning up.
That's an excellent way to put it. They are the ecosystem stabilizers. By consuming those acids, they bring the pH back up toward neutral. If they don't do their job, the waste just stays stuck in that highly acidic, toxic, putrefying phase.
Let's shift gears now. All that hidden chemistry, it translates directly into what we see, touch, and smell. So structural collapse. Why does a firm apple turn into that signature mushy, water-soaked mess?
That is often driven by bacterial soft rot. Bacteria like Pectobacterium are masters of this. They secrete these highly targeted pectinolytic enzymes.
Which attack the pectin.
Exactly. Pectin is the biological glue that holds plant cells together. When that glue is dissolved, the cells separate, a process called maceration. The whole structure just collapses into what the sources elegantly call a pool of its own juices.
And as it liquefies, it gets thick. It's not just dirty water, it's viscous.
That viscosity is due to extracellular polymeric substances, or EPS. Think of it as biological infrastructure. It's a sticky matrix of polysaccharides and proteins that bacteria secrete to build their communities.
Like a slime city.
A living slime city, exactly. And it's great at trapping gas bubbles.
I've also noticed this iridescent rainbow-colored sheen on puddles in bins. I always just assumed it was oil.
A fascinating and very common misconception. Our sources detail that this is frequently a bacterial sheen, often from iron bacteria like Leptothrix discophony.
Iron bacteria.
They oxidize dissolved iron, creating a microscopically thin film of iron oxide that floats. And because the thin film interference, it reflects light in that oily, iridescent pattern.
So how would you tell the difference between that bacterial film and actual petroleum?
There's a simple physical test. If you poke it with a stick, a bacterial sheen will shatter into jagged, rigid pieces, like cracking a thin layer of ice. It won't reform.
But an oil slick would.
An oil slick will swirl and then flow back together smoothly. It's a little chromatic map telling you about active metal oxidizing bacteria.
Incredible. Now for the most visceral part, the olfactory symphony. These volatile organic compounds, the smells are nature's warning system.
And they are so potent because our noses can detect them at extremely low thresholds, down to parts per billion. The heavy hitters come from the sulfur cycle. You get methanethiol, which is that rotting cabbage or dirty sock smell, and of course hydrogen sulfide, the classic rotten egg.
And then there's the truly repulsive stuff from the nitrogen cycle, the scent of rotting animal matter.
That's from protein degradation. It releases diamines like putrescine and cadaverine.
Aptly named.
Very. They provide that rank, heavy, foul, animalistic smell. On top of that, you get ammonia, which doesn't just smell. It causes a sharp, stinging, painful sensation in your nose. That's called trigeminal irritation.
The sources mention something called the fermentation paradox, that sickly sweet odor mixed in with all the foulness. It's a really confusing, repellent smell.
It's chemical dissonance. It's uniquely nauseating to us. The fermenting sugars produce sweet esters, which have fruity or solvent-like notes. But when those sweet notes are mixed with heavy sulfur compounds and sharp nauseating amines,
the brain gets conflicting signals.
Exactly. The sweet says food, but the amines say toxicity and death. That conflict is what makes the smell uniquely revulsive.
So once the microscopic banquet has begun, it attracts the macro-colonizers. Let's talk about the blowfly maggot mass. It's described as a biological machine.
It truly is an engineering marvel. I mean, an individual maggot is cold-blooded, but the collective mass acts as a homeothermic superorganism.
Meaning it generates its own heat.
A lot of heat. Their collective metabolic activity can raise the internal temperature 10 to 20 degrees Celsius above ambient. You can reach 50 degrees Celsius or more.
A 50-degree maggot mass. Why are they doing that? It must be costly, energetically.
It serves two critical purposes. First, it massively accelerates their digestion and growth, lets them consume biomass incredibly fast. Second, and just as important, it's a thermal exclusion zone. Most competing bacteria and fungi can't survive at 50 degrees.
So they're monopolizing the resource.
They're cooking out the competition.
What I found equally fascinating was the acoustic signature of rot. The sheer number of organisms makes an audible sound.
Absolutely. It's the friction of thousands of bodies rubbing together and the rapid action of their mouth hooks tearing tissue. It's described as a distinct crackling, clicking, or popping, very similar to Rice Krispies in milk.
Wow.
Forensic entomologists can actually use that sound to estimate activity levels in a decomposing matrix.
Meanwhile, burrowing underneath all this, we have the cockroach, tenacious scavengers.
And they are highly thigmotactic.
Meaning they like tight spaces.
They're driven to seek physical contact, so layered waste is a perfect habitat. And they're attracted to those VFAs, the sour smells of the fermenting sludge.
And this is where they become notorious mechanical vectors for disease, right? Because of their greasy coating.
Their body coating, made of cuticular hydrocarbons, it acts like a magnet. It traps pathogens like Salmonella and E. coli, which are thriving in the waste. And because they move so easily between that banquet of rot and our living spaces, they transfer these pathogens mechanically, on their feet, through regurgitation, defecation.
Okay, finally, we get to the concentrated essence of the whole process, the fluid legacy, also known as bin juice or leachate.
Leachate is chemically dynamic. Young leachate is highly acidic, down to a pH of 4 or 6 because of all those volatile fatty acids.
So that acidity is dangerous.
It's intensely corrosive, and it carries a huge environmental risk because it solubilizes toxic heavy metals, lead, cadmium, arsenic, making them highly bioavailable, easily absorbed into groundwater.
And how does that differ from old stabilized leachate?
In old leachate, the methanogens have done their work. The pH is stabilized, often alkaline, above 7.5, but it's still highly toxic because of extreme concentrations of ammonia and other stable organic compounds.
So the ultimate fate of all this, if nature is allowed to run its course, is stabilization through humification.
Yes, and this is why terminal stable waste is always black. That color comes from the synthesis of dark, complex organic molecules called humic substances, humic and fulvic acids.
Stuff that makes good soil.
Exactly what gives rich soil its dark, fertile appearance. When they return to the soil, they improve water retention, they chelate metals, they effectively mark the completion of the ecological cycle.
So we started with just, a simple act of discarding food, and we've traced its journey from organized, low-entropy energy to thermodynamic chaos. It's all guided by enzymatic warfare, resulting in this fascinating sensory output of smell, color, sound, and heat.
What we dismiss as waste is recognized by nature as an immensely energy-rich resource. The anatomy of decomposition just demonstrates relentless efficiency. Nature doesn't waste energy. It uses a cascade of scavengers to ensure everything is recycled.
And that brings us to our final thought for you to think about. In the perfect natural cycle, humification produces fertile soil. It completes the loop. However, our modern waste systems, they're designed to arrest this process. We seal this potent energy source and these valuable humic compounds into plastic-lined landfills. We stop the cycle from finishing.
So instead of stabilization,
We're left with a toxic, lingering legacy of corrosive leachate and continuously escaping methane. So what does it tell us about the ultimate efficiency and organization of human systems when we deliberately prevent nature's most fundamental regenerative processes from completing?